This is podcast number 67, and this is the second part in the Bladeless Wind Turbine podcast. So the podcast number 66, the one before this, is the first part. If you haven't watched that or listened to that, go back and listen to that and then come back to here. So in the first part, we talked about how these things work. So we're all familiar with how regular wind turbines work with the blades, but this one was without blades. And we also talked about how some CFD simulations they did on bladeless wind turbines just to show how different geometries affect their energy extraction. So to look further into the experimental side, we're also going to be looking at the rest of this paper called Design and Development of Bladeless Vibration-Based Piezoelectric Energy Harvesting Wind Turbines. And this is open access. You can find it in the link in the description. But first, let's quickly go through just a recap on how these things work. So unlike a regular wind turbine that has blades, these do not have blades. They utilize the von Karman streets, so shedding of vortices from each side of a cylinder or a bluff body periodically, which then creates this vibration, and this vibration is then attached to the vibration goes through the central object, and then that object has piezoelectric sensors attached to them, and then those piezoelectric sensors, when they get flexed, they then create electricity, and that electricity is then how you produce the power or the electrical power. So you effectively extract the vibrational energy from the flow and then you convert it into electrical power. So that's how the principle of it. And they looked at a few different geometries, from a typical cross-sectional circular one to a cross-sectional circular one with like little fins coming off there, and a certain number of them, so 4 or even 6. And that was all for CFD. Now let's look into the experimental setup. So they used a piezoelectric sensor. They attached it to the design's mast at 3 locations. So you have this central shaft, which they call the mast. Then on top, you would typically have this object, which is the cross section could be cylindrical, or could be cylindrical with these little fins coming out or whatever. And so to determine how to actually extract energy to begin with, you need to attach the piezoelectric sensor somewhere along the mast. So they did it at 3 different locations to see how that would affect the electrical output, which is at the top, middle, and bottom of the mast. And the sensors were connected to voltmeters to read the exact voltage, and that represents the power. So they looked at if there's more voltage coming out of it, then that means there's more power. And they also looked at the mast angle. So they have this entire bladeless wind turbine, and the mast angle is the angle between the central shaft and then the flow. And they looked at 2 different angles, 0 degrees and 5 degrees. And one reason why they looked at this was because they wanted to see how wide a window of operation this bladeless wind turbine could operate in. And this is something we talked about in the previous podcast, number 66, where these bladeless wind turbines have been around for quite a while. But one major problem with them is that they can only really operate in a very narrow window of velocities. And that's because we're really banking on the resonance frequency to create a lot of the electrical power. So if you're outside that resonance range, then it won't work very well. So one way that they can extend the resonance range is by changing the stiffness and damping of the central mast itself. But that's in podcast number 66. From here, we're looking at 2 different angles of attack, and I wanted to see how these different angles affect the lift force and hence the harvested power. So the prototypes of these designs that they're looking at, they have a simple cylinder and a modified cylinder, and they're placed in an open loop wind tunnel. So let's have a quick look at what these look like. So the simple cylinder is exactly what you think. Like, it has, in total, the entire thing is probably about 15 inches tall, so about 40 centimeters tall. And then the top part, so about the top third, has this cylinder part, and it either has a very simple cross section, it's just a circular one, or it has the exact same cylindrical cross section, but then it has these little like poles sticking out of it to change how the vortices shed off the actual object. And then at the mast, they have different locations of the piezoelectric sensor, as we mentioned. And they say that the proposed prototypes were exposed to an airstream with different flow speeds, starting from 1 meter per second up to 25 meters per second. However, the main focus is between 5 meters per second to 20 meters per second. And the results are that, as predicted by the numerical results, increasing the velocity increased the amount of applied force on the vortex generator. So that means that if you have a greater force, you have greater flex, and that means you get a greater change in the voltage on the piezoelectric component. That means more power. They also say that furthermore, adding complexity increases the lift force slightly. So what they're talking about here is by making the cylindrical part more complex, they're saying it increases the lift force slightly. Now, whether this is like a universal law, like if you just make something more complex, it's always going to do this or not, it remains to be seen. I would suggest probably not. It won't be a universal law. I think that maybe it's just in this particular case it did. So increasing complexity may not always work, I don't think, but here they're saying that for this particular case it definitely did. If you know any more about it, let me know as well in the comments. It'll be interesting to find out. So they say placing the piezoelectric component farther from the vortex generator induces more electrical voltage in the piezoelectric element. So they're saying, generally speaking, if you put the piezoelectric sensor the furthest away that you can from the actual part that is having this vortex shedding, that's going to increase the amount of power that you can get, because it's going to flex the most compared to that point. Nevertheless, this phenomenon cannot be observed when the piezoelectric member is in the middle of the mast. So that's interesting. Even though if you put it very far away, you're getting a lot more power. Putting it in the middle section, it doesn't necessarily increase the amount of power that you're getting. And that's probably because the mast is probably doing the most flexing at the point where it's attached to the ground. So if you think about the entire beam, sure, it will be flexing as you go along, but the most strain will probably be around where it connects to the ground. So the mast becomes an obstacle in the turbulent flow, which is neglected in the numerical simulation, whereas in the experiments, it's not neglected. So that results in a different effect for this amount of electricity you can get. And what they're talking about here is, in the numerical simulations, some of the trends that they found weren't the same as here. For example, this where you place the piezoelectric sensor. They say this effect probably affects the wind flow around the mast and the vortex generator object and enhances the vibrations of this part of the mast. So unlike the numerical simulations where it wasn't really fixed to the ground, that changes the flow physics a little bit, because now this vortex generator is going to be bending differently if you do attach it to the ground and you have that boundary condition. Additionally, considering a constraint for the mast movement and fixing the mast to the ground changes the mast vibration pattern. So again, compared to the experiments where you are fixing it to the ground, and in the numerical simulations you're not, the vibration pattern is going to be different. So that means that the power output is going to be different. Finally, it should be noted that the angle of attack almost does not impact the exerted lift force. So that's not that surprising to some extent. So the reason why there are two potential reasons why changing the angle of attack could affect the amount of lift that you're generating and then the amount of power that you're generating. So the first one is that if you have the mast at a different angle of attack, that central beam might affect the flow differently when it's at 5 degrees compared to 0 degrees. Now, the other interesting thing is that if you have the beam at 5 degrees to the flow, it means the lift force that is actually produced by the cylinder is not in the same direction as the weakest point, the weakest flexing point of the beam. So in technical terms, the direction that the second moment of inertia is the smallest is not now aligned with the direction of the lift force. So that means that the beam won't flex as much if you have it at an angle compared to if you have it aligned. Now, how does that affect the power? Here they said it's not as effective as you'd expect, perhaps. But if you change a great angle attack, I reckon it might result in a lot more of a change, because if you have a beam and you change it so the direction with the highest second moment of inertia, so the highest stiffness, is in the direction that the lift is being generated in, it means that the mast is not going to flex nearly as much. So that means that there's less flex, which means that there's less electricity being induced in the piezoelectric sensor, and that means that you're not getting as much power. So I think the angle of attack could make a difference, just if it's much greater than what it was. 0 degrees compared to 5 degrees is not that much, and when you look at the cosine of that, it's going to have almost no change on the resulting force. So that's probably why they didn't see too much of an effect here. Now, interestingly, they have the calculated power attained for the piezoelectric component located at the top of the mast and also at the bottom of the mast. So they compared these two. And they have 9 different cases. They have 3 cases where it's a simple cylinder at 10, 15, and 20 meters per second. Then a modified cylinder, so the one with the like little tab, the fins coming out of there, at again the 10, 15, and 20 meters per second. And finally, the modified cylinder, but with the real life dimensions at 10, 15, and 20, 10, 15, and 20 meters per second. They have a typo here, but I'm pretty sure they mean 20 meters per second. And generally speaking, the trends that occur are that as you increase the velocity, the amount of power that you can extract increases dramatically. So, for example, in the simple cylinder situation where it's just a very regular circular cross section, at 10 meters per second, the amount of power that you can obtain is like only 1/30th at 20 meters per second. So even though you've only doubled the velocity, the amount of power you're obtaining is 30 times the amount, or even more, probably 40 times almost. Interestingly, between 50 meters per second and 20 meters per second, the amount of power that you obtain is 4 times the amount. So it's only a 5 meter per second increase, but it's a lot more power that you're obtaining. And these general increases are typical for each one of these cases. So it doesn't really matter whether it's a simple cylinder, modified cylinder, or the modified cylinder with real life dimensions. These jumps in amount of power that you're obtaining is fairly consistent. And that's at the top of the cylinder, at the top of the mast, sorry. When you put the piezoelectric component at the bottom of the mast, they also have some results for this. You get a similar result again, where if you increase the velocity only double, you get a lot more power, like about 30 times the amount. And in some cases, it seems like you can even get more than that, maybe 100 times the amount. So putting the piezoelectric sensor at the bottom of the mast potentially has an even greater dependency on the velocity. So increasing the velocity by a little bit has an even greater effect on the amount of power you can get out when the sensor is at the bottom of the mast. They say it is evident from these results that placing the piezoelectric component as far as possible from the vortex generator, so at the bottom of the mast, provides more attainable power for the piezoelectric component. So that's also true. If we look at, let's say, case 9, which is the modified cylinder at real life dimensions at 20 meters per second, the amount of power that can be obtained is 212 nanowatts when the sensor is at the bottom of the mast. When it's at the top of the mast, that's only 3 nanowatts. So putting it from the top to the bottom increases the amount of power by, 70 times? So that's a huge amount. And that's because there's probably a lot more flexing going on at the bottom of the mast. They say, as was expected, high wind velocity with the effect of adding complexity to the geometry, which are the contributing factors in the lift coefficient increase, positively affect the generated power by the piezoelectric component. So, in addition to that, they have the effects of the wind speed on the output voltage, which is directly indicative of the amount of power, and also the lift and drag forces. And they put them, and they have the top sensor, middle sensor, and bottom sensor locations plotted with the output voltage. So, first of all, increasing the wind speed actually reduces the lift force. So that's quite interesting. If you have 5 meters per second for the simple cylinder case, so it's just a regular circular cross section, the lift is about 5 newtons. If you increase that velocity to 25 meters per second, the lift drops to 2.8 newtons. So it's a dramatic drop, about half. Interestingly, the drag force doesn't really change too much. At 5 meters per second, the drag is about 2 newtons. And then when you get to 2.25 meters per second, the drag is about 2.1 newtons. So it's not too much at all. And I don't really know what the error bar is here either. So the drag force does not change too much with the changing wind speed, but the lift force does, and it drops. Now, going on to the location of the sensor and its power output at low velocities, the location of the sensor doesn't really affect the amount of power that you're getting out. So it doesn't matter whether it's at the top, middle, or bottom. At 5 meters per second, the output voltage is always around about 3 millivolts. At 10 meters per second, it's now at about 5. But once you get to about 15, then there's a massive deviation between how much power you can get compared to where the sensor is located. So when you get up to 25 meters per second, if you have the sensor at the bottom of the mast, the amount of power you're getting out is about double to triple the other two locations. The middle and the top sensor locations don't really differ too much. Again, once you get to a certain velocity, 20 meters per second here, they do start to deviate a little bit, but even still, it's not that much compared to how much of a deviation the bottom location is. And that's at 0 degrees angle of attack. At 5 degrees angle of attack, very similar things occur. So you have a drop in lift with increasing wind speed. The drag force stays pretty much constant. And once you get to about 15 meters per second, the output voltage from the bottom location dramatically diverges from the other two, and the other two stay fairly close. And the amount of power that you do get out increases a lot for all locations. It's not just the top, but both the middle and top and bottom as well, all of them. Now, for the complex cylinder, the exact same trends occur again, which is interesting to note. It doesn't matter what the cross-sectional area looks like in this case. The lift and drag trends and then the output voltage trends are again the same. Most notably, well, the most important thing being that once you get to 50 meters per second, the amount of power that you can get out of the bottom location is dramatically more than the other two locations by about a factor of 7 now. And when you put the mast at an angle of attack of 5 degrees, same thing occurs. But interestingly here, the amount of power that you can get out doesn't really change compared to 0 degrees. Whereas for the simple cylinder, we saw a slightly greater increase in the amount of power output by about 50% by changing the angle of attack. So those were the experimental results, and they compare to the CFD results fairly well. There were some differences, most notably that the CFD didn't have that fixed boundary condition at the base. So that affected how the thing flexes and how much power you can get out. So in conclusion, the experimental results show that the location of the piezoelectric sensor influences the amount of generated power. It also showed that it's not really that linear, like putting the sensor right at the top doesn't change too much the amount of power you can get compared to putting it in the middle. But then putting it at the bottom changes dramatically. So it's very non-linear in this case. They say increasing the distance, so that's what they say here. But also increasing the velocity also changes the amount of power as well, and non-linearly. So doubling the velocity more than double the power output is sometimes 10, even 100 times the amount of power that you can get out. So that's in this podcast. Make sure to like, subscribe. And if you're doing experiments or you're doing experiments to get validation data for your CFD, you want to make sure that you measure the atmospheric pressure, the barometric pressure, the humidity, and temperature. That way you can calculate the density. We have the Atmosphere Hawk. It actually does that for you, so you don't have to worry about it. And all of our clients really love it. Link in the description, get one for yourself to make your experiments more accurate and better. I'll see you next podcast. Peace out, amigos.